So I wanted to share with you some data that we're currently awash in. And even though the coronavirus situation is the cause of the fact that we're not together in class and is currently probably more than we're hearing about it more than we want to, it's too good an opportunity to miss. Um, Coronavirus, like any um, infectious disease spreads according to certain rules. When we model this sort of thing, and this isn't a class in modeling, but we have a modeling class and we've done disease propagation before. Basically, the rate at which a disease progresses um, is dependent on three things, really only one of which we have control over. We really have three groups of people. Those people who are susceptible to the disease, we usually assume those are the people that haven't been infected yet. Those people who currently are infected and are shedding the disease are contagious, and that's the second group. And the third group are the people who are recovered. And we assume that people who are recovered have sort of two properties. Both, one, they're not shedding the disease anymore. They're not contagious. And secondly, that they have immunity, at least for a while. We don't know how long people who have had coronavirus have immunity. It may be forever. It may be for several years. It may only be for a few months. But we're assuming that they're immune for at least a little while. So we have these three groups of people: those who are susceptible, those who are contagious, and those who have recovered and are no longer susceptible or contagious. And as the number of initially, when you have an outbreak of a disease, you have a small contagious group, and you have a, a, a large group of people who are susceptible, basically everybody, and you have a small group of people who have recovered and are no longer contagious and are no longer susceptible. And near the end of that whole disease propagation, things have sort of reversed. We have a small group of people who are still susceptible and a large group of people who are recovered. Um, Now, really, the only thing we have control over is how much contact there is between the contagious group and the susceptible group. The more contact there is, the faster the disease propagates. And we could build up a model. If this was a modeling class, we could build up a model. It's a very interesting thing to do, to watch disease progress, but this is not really part of this course. Instead, I wanted to take a look at the actual statistics. And here's one site that I've been using pretty extensively. So worldometers.info. You may have your own favorite site. I don't know if you're totally as fascinated with numbers as I am, but when I'm in a situation that makes me nervous or gives me anxiety, I basically have to immerse myself in the situation as much as I can to understand, and that makes me feel better. And for me, that's often a matter of immersing myself in the numbers. So I'm going to click on this site, the Worldometers info, and what we have here is on this page the number of coronaviruses cases globally. Right now we're approaching 500,000 cases. About 22,000 people have regrettably died, and about 117,000 people have recovered. Now, I need to point out that our information is very imperfect here. We actually don't know how many people are infected, because there may be a large number of people who are infected that we don't know about. Ironically, this is the biggest piece of information missing from our modeling right now. Sorry about the ads on the right. I usually don't have ads in my lectures, but unfortunately there are ads in this one. Um, so Unfortunately, the biggest piece of information we're missing in terms of our model is not about how contagious this thing is. It's about how many people are currently infected. And ironically, it's the larger number of people that are infected, the better, because that means that more people already have it, and the cases that are actually serious are a smaller percentage of the cases of the total number of people who actually have this thing. And so hopefully in the days and the weeks that are to come, we'll have a better idea about that. But again, that goes back to the modeling. You might have been reading about the Oxford model versus other models, and even though the situation is serious, depending on which model turns out to be closer to the truth, it will ultimately be serious to a different degree. And I might have some suspicions, but I'm certainly not going to share them with you. I'd much rather you came up with your own conclusions. All we're going to look at is the data that we have. So let's click on countries here at the top of the page where you see case graphs, death graphs, countries. You can look at the site yourself at your leisure. I've spent hours poring over it in addition to other sites. So we're going to go to countries. And we see the countries now ranked according to the total cases that they have. You can see China is still number one, and Italy is number two. China's had over 80,000 cases, but its caseload is going up fairly slowly at this point. USA is number three in terms of total cases that it's had. If we click on active cases and sort this thing by active cases, you can see that USA is actually number one now. The United States has more active cases of coronavirus, more so as far as we know, that in terms of the actual cases that are being recorded, and as I said, there may be many, many cases that are not recorded in the United States and outside the United States, but the United States has been particularly sluggish in getting testing out there. But these are the confirmed cases. We have more confirmed cases than any other country in the world right now. We're actually, of course, a substantially larger country than Italy, which is number two. I want to click on the USA right now. So I'm going to click on USA. And nothing's happening. Let me click on USA again. There we go. And here we have the total number of coronavirus cases in the USA, the total number of deaths from coronavirus in the USA. We have a much better idea about deaths than we do about total number of cases. And here we are, 428 people who have had coronavirus and have recovered. They break it down by state, which might be of interest to you, but we're actually going to go down here to where we have the total number of cases. And you see a curve whose shape you probably recognize. That looks a lot like an exponential growth curve. And you've seen exponential growth curves before. We talked a little bit about how diseases propagate earlier. So in the early days, when you have a small number of contagious people, then, if the number of contagious people double, the number of contacts between contagious people and susceptible people are going to double, because if the group of contagious people is still relatively a small portion of the total population, then the number of susceptible people is still pretty much the same, even after the number of contagious people doubles. Later on in the outbreak, things change because the number of susceptible people, as proportionally, starts to substantially shrink, and you don't get exponential growth forever. You can see on where we have total cases, right now it says linear, and you can see 20,000 people, 40,000 people, 60,000 people, 80,000 people equally spaced. I want to click on logarithmic because this will give us an idea of what we're going to do if we want to model exponential growth. I'm going to click on logarithmic. Now, ignore all the noise at the beginning of this curve where we have few people infected, and of course we have very little testing there. I want to look more or less at the last half of this curve, and it looks a lot like a straight line. And if you have an exponential curve and you take the logarithm of the y values and then you plot that, you get a straight line. And so this gives us an idea of how we can do exponential regression. We've already done linear regression, we've done quadratic regression, and we're going to do a case of exponential regression. And we're going to pick the data right off of here. I'm going to explain how to do this when I post the homework assignment. But you can see that this is a straight line. And so if you have something like a disease propagation, and if you look at it linearly, of course, we can see basically what's going on in terms of the total number of cases. And again, it's a little hard to read this because at first we weren't testing a lot of people, and now we're testing more people. We have a slightly better idea. Hopefully in a week we'll have a better idea yet. But we have basically this straight line, which means that our cases are increasing approximately exponentially, which means the um, isolation that we've put into effect is not serious enough to really have put a dent in the propagation of this disease yet. I want to take a look at some other countries. We could look down at the new daily cases, and we could look down at the current active cases, and we could look at the total number of deaths. And you can see again, when we look at the total number of deaths, you see what looks a little like an exponential curve. If we click on logarithmic, you can see again that later portion of the line looks a lot like a straight line, so we're not having too much of an effect yet. Let's go back to the list of countries. I must be fighting with bandwidth. Come on. Sorry about the delay. There we go. So let's go back to the list of countries. And this time let's click on Italy. So Italy is having a very bad time with this right now. And we'll go to the total number of cases in Italy. And here you can see a curve which certainly looks exponential for a little while, and then it's still increasing, but it starts to straighten out. Let's look at this logarithmically. You can see that this is no longer a straight line. So Italy's control is starting to have an effect. We're bending that straight line down. That's exactly what we want to do. When we look on a logarithmic scale, we want to bend this curve down. Oh gosh, there we go. I'm going to get these ads off the page because they're so distracting. So we start to bend that line down, and that's exactly what we want to see. We want to have our mitigation efforts to make the growth no longer logarithmic. So we can see if we put this on linearly, the number of cases is still increasing, but it seems to be increasing no longer exponentially, and we can see this when we take the logarithm of these values. You can see when we take the logarithm of the values, if you look on the left where the total number of cases is, you can see that these things, what are spaced evenly now, are the powers of 10. The distance from 1 to 100 is the same as the distance from 100 to 10,000. So each one of these bars is a 100-fold growth. And so we want to bend this thing down. And if we take a look at new cases, active cases, total deaths in Italy, so we'll take a look at the total deaths picture, and you can see that that's still increasing, which is scary. If we put this on a logarithmic scale, you can see that they are actually having an effect. They're bending this line down, which is what we want to see. Let's go to yet another country. And we'll go to China, which was where the outbreak first was. And they have put into effect more serious isolation protocols than we have. Let's see what's going on there. Okay, here's the total number of cases in China. And you can see we don't even have to go to a logarithmic scale here. You can see that they've had a serious effect on the total number of cases in China. By the way, if you take a look at this curve, I think we've all seen this shape of curve before. This is a sigmoid curve, which sort of increases and then increases very quickly and then sort of levels off. We saw this kind of curve when we were doing logistic modeling. So these things come in. If we put this on logarithmic, I don't know if we're going to see anything much more instructive. But you can see that they've had a serious effect. Now, unfortunately, we're not 100% sure we can trust the numbers out of China, But let's go on this is just the data that we have right now, and let's just go with this. And you can see that um, here we have the active cases in China, and so you can see that that's increased for a while and then decreased, assuming we can trust all that. And the total deaths in China, you can see that it started growing exponentially, and they were able to bend down that curve. And this has a very nice sigmoid shape. Uh, and so these curves that we've seen before are certainly all present here. Let's go to the total number of cases in the world. So here we are with the total number of cases in the world. You can see that this is a very complicated shape that we have right here, although the end, unfortunately, looks like it's growing exponentially right now. This model that we have right here, this in this picture, involves a lot of different interesting factors that are difficult to put into a model. The fact that we're talking about spread not just amongst one community, but across a variety of different communities, and those communities are reacting differently, which is why you have this very interesting shape. If we put this on logarithmic, we see something that we really don't want to see. The end of this curve, not only is it not curving downwards, it's actually curving upwards right now. So that's definitely not what we want. I'm not trying to make any predictions as to what's going to happen in the future. I'm sure you are again awash in information right now, and I don't want to sort of contribute to any more of that. But all I want to do is expose you to the data, and we're going to do a little bit of exponential regression. And this is a very interesting set of data for me. And as I said, when I get nervous about something, the data is often what makes me feel like I have more of a handle on it.